How do you decide if a differential equation is exact? How do you solve an exact differential equation is really the question I'm trying to pose here. I think separation of variables and also the integrating factor technique, these are kind of direct, very calculus-style derivations, right? Now I'm starting to use a little theory here for this exact part, and I think that's why students start to lose track sometimes. Let me just give you an example. I mean, these examples were backwards. I put the cart before the horse, right? I started with the solution, and I found the differential equation which it satisfies, right? This is basically implicit differentiation from calculus 1 in a different notation. Here's a different one, though. Let's suppose that xy squared dx plus x squared y dy equals to 0. Let's try to solve this. Solve if possible. Well, let me scratch that if possible from the record. It's pretty hard for me to come up with examples of differential equations we can't solve for reasons I'll project soon. But the real question is this exact? Right? So if it's exact, what we're trying to do is we're trying to make this partial f partial x. We're trying to make that partial f partial y for some level function f. Now, we've dealt with this problem in calculus 3, right? This is that conservative vector field calculation. Given a conservative vector field, can you find a potential function, right? Remember that? This is equivalent to the calculation. I have the vector field f equals to xy squared, x squared y, right? I'm asking, is it nabla little f, right? Where this is what? Actually, let me call it big F. Partial f partial x, partial f partial y. I mean, it's the same calculus problem. The problem of exact differential equations is very much connected to conservative vector fields. I won't try to explain that today. Spirit leads me tomorrow, I'll do it. But there's some discussion in my notes, of course. But okay, so how do you do this? I mean, we're trying to solve partial f partial x equals to xy squared, and partial f partial y equals to x squared y. I mean, technically speaking, this is a system of partial differential equations, but they're harmless, all right? So what you do is you integrate, at least, I mean, there's various methods, but here's one method. Just integrate both, one with respect to x, the other with respect to y, and use some common sense to find the solution from those, right? So if I integrate this with respect to x, what do I get? I get 1/2 x squared y squared plus some constant function of y, right? And if I integrate this with respect to y, what do I get? I get 1/2 x squared y squared plus c2 of x, right? Now, the mistake students sometimes make is just to add these. That's just silly, right? You should pick the common terms and then check your answer by taking the total differential, right? So I take these two things, I look at them, I go, aha! So this tells me that I should use f equals to 1/2 x squared y squared. That's a good level function. If I take the total differential of this, let's check what happens when I take the total differential of that. df is what? It's 1/2 of 2xy squared dx plus 1/2 x squared of 2y dy. In other words, it's xy squared dx plus x squared y dy. Hooray. So I get back that the original differential equation is nothing more than what? So what I'm trying to argue here, guys, is if we go back to the original differential equation, we can rewrite this, right? This differential equation is the same as what? It's the same as df equals to 0, where f is equal to what? 1/2 x squared y squared, right? The solution to that is what? I mean, what does that say? It says the solution is 1/2 x squared y squared equals to a constant. So that's it. So the method of exact equations is what? Find a level function for the differential equation. Claim that the solution is the level function equal to constant. That's the method. Now, is every differential equation exact? It's not the case, all right? Just like every vector field is not conservative, right? There's lots of vector fields which have path dependence, which have the line integral around a loop not being 0, right? Lots of differential equations are not exact. And so, we have to deal with that. So it's useful to find a simple criteria for when it's going to be exact and when it's not going to be exact. Let's see here. Let's see if we can, maybe you guys can discover it with me. And we'll take a break here. So, let's think about this. So we have m would be partial f partial x, right? And n is partial f partial y. So you guys tell me, what would happen if I calculate partial m partial y? What would that be equal to? Right? But what do we know about partial derivatives? Does it matter if you take partial y partial x or partial x partial y, like the order? Remember, the order is immaterial. We should get the same answer. So we can flip the order of the partial derivatives, right? They commute. So calculus says, for nice enough functions, which are the kind we're looking for, this is true, right? But what is that? What's partial f partial y? N, right. So this would be partial n partial x. So exactness test, we need that partial m partial y is equal to partial n partial x on u, a subset of R2 for m dx plus n dy equal to 0 to be exact on u. Now there's a little bit of topological fine print here. This u, to be careful, this u has to look something like this. No holes, right? If u has to be simply connected, And then if it is simply connected, then the solution sets to this differential equation, they're just going to look like, I don't know what they're going to look like exactly, but they could be, they're going to be in here. And they're going to fill out the u as level curves of this function, which you can find. We can prove this by Green's theorem. Green's theorem requires that the u is simply connected. In other words, it has no holes. Otherwise, bad things happen. I don't know how far you guys got into conservative vector fields in your Calculus 3. You may or may not have been exposed to these subtleties. And it's okay. It's not really what we're after in here at the moment. So I'm just going to tell you, if you have partial m partial y equal to partial n partial x on a simply connected domain, then it's exact. On the other hand, if you have that partial m partial y is not equal to partial n partial x, game over. It's not an exact differential equation. You got to try one of the other two methods. Separation of variables or integrating factor technique, okay, or substitutions. But so let's see here, example 13, just to show you what that looks like. If I had something like x dx minus xy dy equals to 0, well, that would be troublesome. See, because here, this is my m, this is my n, partial m, partial y equals to 0, but partial n, partial x is equal to what? Minus y, but yeah. These are not equal. That's not an exact equation. What that means, again, so that means that this, right, is not equal to df for some function f. And so I can't just say, oh, that's df, and f equals to a constant, it's the solution set. Now, there's a theorem, and then we'll take a break. Pfaff's theorem says something that's kind of, oh, it's just really greedy. It says that basically any differential equation you look at, I forget the fine print. There is some fine print on this theorem, but essentially Pfaff's theorem says, if you have m dx plus n dy equals to 0, then there exists I such that im dx plus in dy equals to 0 is exact. So what it says is that while your given differential equation, like this one, is not exact, you can find some function I that when you multiply the differential equation by it, it turns it into an exact equation. So like a really neat example of that is if we start with dy dx plus py equals to q, and we try to ask, is this an exact differential equation? Is this exact, right? That's the standard linear differential equation in standard form, right? If I rewrite this in Pfaffian form, what is it? It's py dx plus dy equals to q dx, which I can rewrite as what? Py minus q dx plus dy equals to 0, right? So is the linear differential equation rewritten in Pfaffian form, is it an exact differential equation? Can you guys, is it? Here's my m, n is equal to 1, right? So what's partial m partial y? P is a function of x, q is a function of x, right? So partial differentiating that with respect to y just gives me p. And of course, p is not usually going to be equal to partial n partial x, which is 0, right? But Pfaff's theorem says you can find some I that if you multiply the, let me give it a name, you multiply star by I, it makes it into an exact differential equation. Like you can take this thing here and make it exact by multiplying by I. That I is exactly the integrating factor. But you can sort of be generic. You could say, okay, so I want I py minus q dx plus I dy equals 0 to be exact. All right? And we can be greedy. We can say I is equal to function of x alone. If we do that, then what condition does I have to meet according to this theorem we just found? So this would be my new m, right? This is my new n. So what's partial m? Partial y is what? So I'm saying, suppose I is just a function of x. When you take the partial derivative of this with respect to y, what do you get? The q and the I goes away, that's constant. We just get IP. What's partial n, partial x? Well, it's just di dx, because we're assuming I is just a function of x. Right? So we have to solve di dx equals to IP if we want this to be exact. What's that? That's di over I equals to p dx. Voila. The natural log of the absolute value of I is equal to the integral of p dx, aka I is equal to the exponential of the integral of p dx. And so there you go. That in some sense is a derivation of the integrating factor. It begs another question. Why do you look for integrating factors? Well, that's a deeper question I can't answer in here. But this is a technique which is known. Multiply a differential equation by something to try to make it nicer. Exact equations are very nice. So finding an integrating factor is a really, really nice thing. This is not a skill I expect you to acquire. All right? I don't think that it's a reasonable request for you guys to learn the general technique of how to find integrating factors for differential equations. This is a much more difficult question than the one I'm asking you to solve. I want you to be able to, here, I give you a differential equation, you decide, can I use separation of variables? Can I use integrating factor technique? Is it exact? And you proceed accordingly. Or I say, hey, this differential equation is not exact, but but you can find an integrating factor of a particular form. And then you select from that sort of blank template of integrating factor the correct one. So a pretty popular problem is we tell you something like I is equal to x to the a, y to the b, choose a and b, that when you multiply the differential equation it makes it exact. I have some of these solved in the notes. It's a pretty, and there's a section in your book called Special Integrating Factors. I don't cover it in its entirety, but that is actually, you know, an important next step in this game. All right. But again, just back to the basics. To tell if it's exact or not, a quick check. Is partial m partial y equal to partial m partial x? If it is, you're off to the races. You find f equal to a constant. That's the solution set. And so great. Now you guys know how to solve first order differential equations. So that's, I guess that's a win. I'm just kidding. You need to work homework, like at least a couple hours of it, right? Before it sinks in. With that, let's take a little break. When do we end? 1:20. Oh, man. How about we just go another 10 minutes and 5 minutes early? Sound good? Is that better? Yeah. All right. So with that, let me, what follows, so there's, existence and uniqueness is the thing that's left for us to talk about. And it's, these differential equations are not too fragile. They're pretty hard to break. So there's usually if I give you a first order differential equation and I give you an initial condition, there will exist a solution and that solution is going to be unique. So like it's not going to be the case I say solve dy dx equals to this function, right? And y of 0 equals 1. Find me the solution, and like 2 of you get different answers. Like that's not going to happen. There's going to be a single function which solves the differential equation and goes through that point, usually. It takes some work to find counterexamples to that. Let me show you one. By the way, I was more or less giving you a very intuitive explanation for how to solve exact equations. I do have a little bit more of a systematic derivation in the notes. It really goes back to whether or not you understand what a level curve is in Calculus 3, though. So if you don't understand that, it's always going to seem kind of like hocus pocus or something, which if you're not a magician, is probably a bad thing. It's here. Mathematician. Well, let's see here. So here's the theorem. If we have a continuous function on a rectangle, then at least one solution exists for dy dx equals to f of xy. So I'm supposing that this function is continuous on the rectangle, right? So like if f of xy were x over y, and the rectangle contains y equal to 0, es no bueno, right? That would be an example where the theorem wouldn't apply, like we saw earlier. Moreover, these solutions exist on all of R in the sense that they reach the edge of R. So basically, I can draw a little picture here. It's saying if your defining function for the differential equation f is continuous on here, you pick a point, right? There's going to be a unique solution, or unique? Oh, at least one. So it could be, there's going to be a solution, and it will extend at least to the edge, all right? In fact, it could be the case that you have 2 in this theorem. All we're assuming is continuity of the defining function, all right? That's one theorem. Uniqueness of the solution actually stems from having the partial derivative with respect to y at the point non-zero. If you have partial f, partial y non-zero, then there exists a unique solution through that point, right? So if you tack on the condition that partial f, partial y is non-zero in the rectangle, then you'd have a unique solution through each point in the rectangle. Okay, this is a nice theorem which gives us courage to find many solutions. Here's an example of non-uniqueness. What I'm using to plot the solutions here, guys, is called PPlane. That's in MATLAB, which you guys, I don't currently have on my computer, by the way. You guys probably have access to it. You're engineers, right? Engineers in training? I don't know. However you think of yourself. Let's see here. I sometimes think I'm a mathematician. I'm not sure, though. Depends on the day. Let's see here. So this guy right here, dy dx equals to 2 root y. Well, here f is equal to 2 root y. Partial f, partial y is 1 over square root of y. That is definitely not continuous when y is equal to 0, right? Like, it's bad. It's very bad. So we don't expect, so we don't know from the theorem that there will be a unique solution. The theorem's criteria not being satisfied doesn't necessitate that there not be a unique solution. It just says that there might not be a unique solution. Like the previous example, I have partial f, partial y is 0, and yet there is still a unique solution, I think. Ooh, that one's neat. I love that one. Let's see here. Anyway, here's my token non-uniqueness of solutions, right? At this y equals 0, you've got the y equals 0 solution, right? And then how many other solutions, at every point there's another solution that lifts off of it, goes up. So it's very, very much non-unique along that. And then down here, these points, the differential equation is not even defined for, because we have the square root of a negative number, right, for y less than 0. Down here, let's go back. So that's the one thing. The existence and uniqueness theorem, just a word on that. Now, this derivation at the start here, I'll probably go over again tomorrow when I talk about orthogonal trajectories, but there's a nice connection between, well, I'll talk about it tomorrow, so let me leave it for tomorrow. But what I derive there basically is that oh, curses, I can't just look. I guess I can. I'll make up my mind here eventually, guys. I got 4 minutes left, right? So I got to get with it here. And I think we should take longer breaks tomorrow because I'm tired. So this differential equation, x dy plus y dx equal to 0, we solved this, right? We solved it using separation of variables to start with. You could easily solve this using exact equations, right? Because like this is the differential of 1/2 x squared plus 1/2 y squared. That's pretty easy to see. So the level function here is 1/2 x squared plus 1/2 y squared. You could guess that without much work. But if you visualize dy dx, these are like little lines that have the slope dy dx given by that. And then so you can draw these little isoclines. You see there's no arrows on them. They just give you the slope. It's like a slope field, right? And then if you sort of connect the dashes tangentially, then that will give you solutions. This is one way to visualize solutions through so-called isocline plot. Let's see here. Here's another isocline field. This one's for dy dx equal to x plus y minus 6 squared. What I'm saying is for the p-plane allows us to plot systems of differential equations, right? So what I'm doing here, guys, is that if I have dy dx equal to like f1 of x, curses. Well, if I have dy dx is equal to f1 over f2, now f1 and f2 can be functions of y and x, and then I'm saying I can solve like dy dt equal to f1 and dx dt equals to f2. There's this p-plane thing. If we put x prime equals to f2, which is, by the way, going to involve x and y. If we put y prime equals to f1 of x and y, then p-plane will create these kinds of plots. All right. So, I mean, technically speaking, this is not quite an iso. I mean, the p-plane thing is giving us something that's a little bit different than the original differential equation because, well, I'll get into it more another day, but I'm kind of cheating to use p-plane to do this in some regard. But anyway, here's pictures of the solutions. As you can see, something really interesting happens along the line when we have x plus y equal to 6. I think that's these things, right? And there's interesting things happen between. And then let's see here. Here's another one. If you look at the direction field, I guess I should really say isocline. I mean, I don't know terminology. I think these are isoclines because there's no arrows, right? So direction fields would have little tangent vectors. I'll get into it tomorrow, the difference. But anyway, here we have a plot of the direction field for the differential equation, and then this p-plane, if you just click on it, it actually plots solutions. So you can actually see what the solution sets look like without actually having to solve the thing. It's really nice. If you just want to see, what do my solutions look like and come to some understanding of what's out there, you can do this without even solving the differential equation. That's especially nice for something like this, which has, this differential equation, we could solve it. Dy dx is equal to y cubed plus x squared y minus x, xy squared plus x cubed plus y minus x. I can actually show you how to solve that using a substitution. Basically change the polar coordinates, then it becomes separable. But, I don't think that's terribly obvious from the outset, is it? But if you chuck this thing into p-plane, it kind of reveals itself in the fact that it has a certain circularity, right? There's some sort of theta. There's some sort of periodicity of the solutions, right? Like if you look at any different angle, it's the same, right? So there's some sort of polar rotational symmetry to the solution set, which suggests that maybe a polar change of variables is the right way to solve it. Anyway, there's just a few examples of direction fields for you. We can play this game. We plot the direction field and then just basically try to connect the dots and use tangential. This is the basis for Euler's method, which I don't really cover in here and I don't test on, but that's an important numerical technique. I'm sure if you take Math 352 from Dr. Wang, he'll talk about Euler's method in there and about how we can use Euler methods to come up with numerical solutions to differential equations. I have little to nothing to say about numerical differential equations in here, so you're safe. It's safe with me. But anyway, I'll see you guys tomorrow. Thanks. Sorry I'm gone 2 minutes over. Oh no, I started 2 minutes late, so I probably owe you. I think I started like 5 minutes late, actually. I probably owe you a few minutes, but I'll behave. Thanks, guys.